All right, welcome back to the afternoon session. It's my honor to introduce Aaron Ames, who is the Brennan Professor of Mechanical and Civil Engineering in Control and Dynamical Systems at Caltech. His research interests span the areas of robotics, nonlinear control, and hybrid systems, with a special focus in developing novel theory and experimentally validating these results on robotic platforms, including legged aerial robots, prostheses, and exoskeletons, with the general goals of achieving safe and autonomous behavior on robotic systems and improving the locomotion capabilities of the mobilely impaired with robotic assisted devices. And with that, I will let Aaron speak.
Great. Thank you for the introduction. It's a pleasure to speak at this workshop. My deepest apologies for not being able to make it in person. But before beginning, I'm going to talk about safe autonomy. Before starting, I want to just note that my students played a huge role in all this work. This is my current lab, and there were 9 of them at ICRA. So hopefully you ran into some of them over the course of the conference. All right, so to kick things off, as everyone in the audience knows, robots are really hard. They fail often and spectacularly, which makes them a lot of fun to work with. But the question becomes, what do we do with this fact that they're hard? How do we ensure safety on robotic systems in this context? So what we'd like to have is this working example of robots all the time. So robots are really awesome when they finally work and things come together. And so this is just one of my students, Xiaobin, walking Cassie around the Caltech campus. And I like this video a lot for multiple reasons. One is you get to see Cassie walking. You've probably seen Cassie in Digit multiple times throughout. But the other reason I love this video is this, where the kid comes from the background and runs up on the robot and tries to catch the robot. And I think this is another aspect of what we do with robotic systems that both makes it exciting because there's this broad appeal of robotic systems, but also makes safety really a critical component. People, humans like to interact with robots, and we need to make this safe. I just want to kind of also note some other highlights. This is just sort of a highlight reel of different behaviors we've gotten in the lab. And it shows that robots are really capable at this point. I mean, what we've been able to do in the last, 10 years, 15 years on advanced robotic systems is quite remarkable. To do these kind of things in a lab on a robot, walking over really complicated terrain, jumping, walking quickly. So robots have great capability, not just in the lab, but outside of the lab. So this is just a shot of, again, Cassie walking with our algorithms around Caltech campus on unknown terrain that has a non-trivial slope on it. And so this shows, again, the capability of robotic systems. And as with everything, though, you see these wonderful videos of robots working right. As you know, with your ICRA videos, you get these great shots that you put with the ICRA paper. But often the world's a bit more complex, and things don't always work exactly as you would expect it to. So this is another video. Okay, this is actually a much earlier video, some older controllers on Cassie. And in this case, the robot spectacularly falls on this root system it wasn't expecting. So the question in terms of safe autonomy becomes, and this is really the thing, is our focus changes from getting robots to do things to making sure they're safe while they're doing those things. And that's where the conversation, again, really changes from stability to safety. And this is what I want to highlight in this talk, is not talk about the controller synthesis, specifically stability or any of those concepts, but rather how we view safety. And what we'd like to have is this video on the top right, where now it's walking over that same root system, but it does so without falling in a safe manner. And so to talk about safety, I'm going to talk specifically about this mathematical construction called control barrier functions. It's a relatively recent invention from about 2014 that has sort of changed my viewpoint of safety in a formal context. So let me start with a little bit of the mathematical background. All right, so what do we mean by safety? So I'm going to be really brief on the mathematical front, but what I mean by safety is the following. First, broadly speaking, take a full nonlinear dynamical system. So everything is nonlinear, but often we'll assume it has affine structure. That is, F and G appear like this, and then you have U, which appears affinely in the dynamics itself. And we have a safe set. So we're going to give a relatively restrictive definition of safety, but I think it's general enough for most purposes. And that's our safe set is defined as a 0 super level set of a function h. So this is kind of illustrated in the figure above, where it's so where the function h is this bowl kind of thing. Our safe set is here, defined as when that bowl is positive. And the question we can ask is, if that is safety, staying within this set, then how can we quantify that safety? And so this becomes a forward invariance question. And this question has really long origins. So the earliest results date back to 1942 and arguably a little bit sooner than this with Ngumu's theorem. And so what happens here is Ngumu's theorem gave us necessary and sufficient conditions for a system to be safe. But these conditions almost always relied on checking conditions on the boundary. But what we're really interested in is, how do we quantify safety looking everywhere in the set? Because this changes the conversation. And so the recent invention from 2014, again, with me and Paulo Taboada and Jesse Grizzle, was we can come up with conditions that are also necessary and sufficient, but now they extend to the entire set. That is, everywhere in the set, you can check the value of this, the derivative of this h function along solutions. And if it's lower bounded by minus some class K function, view this as a constant if you want for simplicity, times h, then you're guaranteed to be forward invariant in that set. And what this does is allow us to synthesize controllers that guarantee safety, specifically optimization-based QP controllers. So what do I mean by this? How does this work? Well, we take our nominal control value, u desired, that's what was running here. And so in this case, safety is the Segway staying upright. And what's happening is my student, Tom, is kicking the Segway, which pushes it outside of its safe operating region, causes it to fall down. So if we instead take that controller that's running here and put it in as u desired, and then enforce a safety constraint on top of that via control barrier function, when we kick it, it no longer leaves a safe region, but rather stays within it for all time. And so this, again, gives us safety via this idea of a safety filter, which is this quadratic program. We can do this with lots of different notions of safety. For example, if safety isn't the Segway staying upright, but the Segway staying in some region in space in the ground. So imagine people are working here. This is a factory environment. Then in this case, without the safety filter, you can make the robot go really unsafe. But with the safety filter, modulating it based on the control barrier function, you can keep the Segway within this safe operating region. So that's the basic mathematical control framework. And this has had a lot of applications that I'm going to just describe some of them briefly. So one example, for example, is the drone flight. So now our safe set is defined as not hitting obstacles in space. So there's onboard camera, onboard sensing, onboard computation here. And when my student moves the obstacle, which is defining the safe region, now it's safe for the drone to move forward. So again, the drone is on a path that would drive it right through the obstacle, but the barrier function prevents that, overrides that command because it would result in unsafe behavior. And when that obstacle is removed, it can continue on with its nominal trajectory unabated. So we've also done this in more complicated obstacles. So the great thing is we don't need to have convex obstacles, convex space. You can just define this over really complicated geometries in really simple form through these functions. And again, here a pilot in this case is trying to drive the drone against these walls, but the barrier function is preventing it from hitting the walls in this context. One more example that I think is really compelling. This was actually presented at ICRA a couple of days ago, which is safe drone flight via geofencing. So this is the same idea as before, but now we've come out of the lab and into a natural environment where now the safety constraint is don't leave regions in space defined by the geofence. And you'll see here, this is the red line showing where that geofence is. And the pilot in this case, just like before, is trying to drive the drone outside of the safe region. And you'll see the value of the barrier function here. So it always remains positive. And the value of the velocity as it hits that wall, the drone slows down in the process. So again, we're able to do this with onboard computation, onboard sensing, in this case using GPS, and at really fast speeds. So it's hard to even show this now at full speed because the drone here is actually traveling at 100 kilometers per hour. So it's going really, really quickly. And we're able to still prevent it from leaving these geofence regions. So that's sort of the basic mathematical framework for safety that I want to sort of underlie the talk on autonomy. So where does this fit in autonomy? Well, let me kind of set the stage a little bit with more complicated robots. So these safety filters are fantastic and work really well, if I can say that about my own work. on lots of different applications. And again, I'm going to show some more examples later. But things get really interesting when you get to more complex robotic systems. So you can still apply barrier functions in this case. So in this case, the application I'm going to show you is what's called stepping stones. So here, the barrier function is that the feet of the robot must land within these yellow pads at every point in time. But because this is a very complex robotic systems, if you just enforce this as is, there's errors in the system that accumulate, modeling errors, et cetera, that causes you to miss these safety critical features. So even though you're enforcing the barrier, you still get on safety because it's a very complicated system. So one solution to this, which is what happens here, is we actually going to learn the residual dynamics in the barrier function. And by learning those dynamics, we can force the system to be safe. So this is where learning and control can start to play a role together. So after just 2 iterations, 2 episodes of learning, we're now landing on these stepping stones every time, which is nice. But I don't think this is the correct answer in general. So you don't want to just deal with this, what I would call a flat robotic system, where the dynamics are viewed in this flat monolithic way, and then you just learn residual dynamics. I mean, again, this is a powerful method, but something happens if you start viewing this from an autonomy perspective. So if you start to view take an autonomy viewpoint on this safety critical control idea and start to put a hierarchy, an autonomy stack into the mix, things get a lot better even without the need for learning. So what I mean by this is what we have now is where we have a small autonomy stack where we have a mid-level trajectory planning layer, which is running a model predictive control problem. And we're passing that to a low-level controller that enforces barrier functions. And we're again doing stepping stones. This is joint work with Hutter and ETH. I heard he gave a great planary with this robot. So you've seen it here at ICRA as well. But we're able to do this stepping stone behavior by merging these two together. Even though the robot's very complex, really complicated dynamics, we don't need learning in this case because we're using this layered approach, where again, the NPC enforces safety constraints, passes it to the low-level controller, which again enforces safety constraints, and these communicate to one another through this autonomy stack. So the reason I'm going here is I'm showing how when you layer things, there's a power to this layering. And this leads to the notion of, in my mind, and the power of autonomy. So the question now becomes, you want safe autonomy. What does safe autonomy mean? And in my mind, it means first acknowledging the role of the autonomy stack in general. What I mean is the role of the different controllers, algorithms, as they play a role in this overall system architecture. And the goal, and the reason I'm showing this video, it's an older video now, but I really like this concept, and this motivated a lot of the work that we've done on autonomy, which is you have a rover on Mars, you have a helicopter, they have to coordinate with one another, pass information back and forth. And how do you understand these really complicated problems where safety is super critical? You have to plan ahead to make sure that they're safe. And again, what I'm saying in showing that graphic is, to me, the key idea is formalizing this autonomy stack. I mean, roboticists use this all the time, but we want to formalize it from a formal perspective and leverage this architecture to make robots do really impressive things. So this is just showing a little video of a robot and walking and then jumping. And the point is, if you do this ad hoc, like on the bottom, you get failures. But if you start to formally synthesize things through this broader autonomy stack using things like motion primitives, all of a sudden you can get much better behavior. And that's really the motivation for this. So let me tie this back now to the safety critical control and show, in my mind, a really powerful example of how leveraging the autonomy stack plays such a powerful role in safe autonomy. And so let's take this example of a drone. And you want to make a drone avoid obstacles in space. This is a very classic problem. And I showed you this example earlier with AV where we did this. Now, the point here is we don't want to have to go in and modify all of the control algorithms and all the different loops happening on the drone, but rather we want to append on a module that will make sure we're safe, working with those existing controllers and not modifying them at all. And the way we do that is we can take a low dimensional representation of the drone. This is what's done, for example, classically in robotics with artificial potential fields and things like that. In this case, we do a single integrator representation of the drone. We synthesize a barrier function for that single integrator representation, which I'm going to call now the trajectory planning layer. We send that safe velocity, that safe reference velocity to the drone, and that's tracked with its onboard controllers. And the important point is this is something that's done all the time in robotics, but what we have here is is a certificate of safety using that layered architecture. What I mean is we can formally guarantee safety on the drone with its existing controllers, assuming there's reasonable tracking. So this was also presented at ICRA this time. And the great thing is once you do this, once you understand and leverage this autonomy stack, even acknowledging the full complicated dynamics of the system, you can do the same thing on a quadruped that you did on the drone. So this is the exact same safety critical controller now running on 2 different platforms with totally different dynamics and morphology, but still in both cases, we get formal guarantees of safety by, again, leveraging this autonomy stack. So this idea is powerful. It goes beyond just those. We've actually have a recent submitted paper, it's still under review, where we can do this on a manipulator too. Same idea. We leverage safety critical control at this mid layer to modulate reference trajectory signals and then pass that to a low level controller. In this case, we have no knowledge of the controller. It's the existing onboard controllers for the arm, and we're able to achieve safe behavior. This is a collaboration with Miso Robotics. So again, I'm just showing these examples of how when we understand the architecture of the autonomy stack, we can get safety much easier than we would if we try to design these controllers from scratch. So this also points to a really powerful way to integrate in learning computer vision into this broader architecture. So in this case, we modify this mid-level barrier function in the autonomy stack, like I mentioned before, to account for the fact that now we have onboard sensing. So what's happening here is we have a quadruped. It has its own onboard walking controllers, also developed by my lab. And then we have a camera system with 3 cameras. And what we're doing is self-supervised learning. This was also presented at ICRA. So this is like a highlight reel of ICRA papers. And we have self-supervised learning that determines the depth of objects in space with those onboard cameras. That depth is then used to calculate the barrier function at the mid-trajectory level planning layer. So we're modulating the forward velocity of the quadruped via a barrier function that accounts for the uncertainty in the sensing via this additive term. And then we pass that down to the low-level controllers, which are our nominal walking controllers. And by doing this, we're able to guarantee safety on the system, even in natural and complicated environments, and even where there's, for example, a human that's stepping in front of it. So this is the barrier function right here, reacting to the human as it walks and then going forward. So again, the autonomy stack lets you do things like fold in computer vision. In this case, we also folded in SLAM. So this is going to appear in L4DC this next month, where we now have an autonomy stack where we're doing simultaneous localization and mapping. We pass this to the barrier function, which then makes sure we don't hit obstacles in space while using our own onboard dynamic walking controllers in the process. So finally, I want to note that there's ways of also taking this safety critical consideration up and down the stack. So initially you saw it down the stack at the low level control level. Then I presented sort of a mid-layer barrier function. You can also do barrier functions at the top layer. And I'll just be brief about this. But for example, if at the top layer you're doing planning with things like POM DPs, you can actually synthesize discrete time barrier functions representing the discrete time dynamical system, which represents the evolution of the POM DP. You can enforce these barrier functions through a very similar sort of thing that we had before, an optimization type problem, and then enforce that at the planning layer to do collision avoidance up top. So now we have barrier functions at the planning layer and sort of safety constraints at the mid layer, maybe via MPC, maybe via a barrier function at that mid layer planning layer. And then you can also do things at the lowest layer, safety critical control, barrier functions there too. And then you can pass these signals up and down the chain. And this starts to now speak to how we can guarantee safety up and down this autonomy stack. And here I return to this example of a drone and a rover coordinated together sort of fictitiously on Mars. But this is kind of where we want to be, is deploying these things in these very safety critical contexts up and down this broader autonomy stack. So finally, in the last just couple minutes of the talk, I want to note that all of the lessons that we learn on autonomy for robotic systems have application in the robotic assisted device space. So in particular, I'm showing here an this is the Wondercraft exoskeleton, which was also at ICRA. Hopefully you got a chance to see it, maybe ride in it. And what we can do is take the lessons we learned on autonomy, and specifically this multi-layer architecture of the autonomy stack, and we can apply methods up and down the stack. In this case, what we're doing is applying preference-based learning to bring the human into the loop, where we can then, after that, apply safety critical control. but we can do preference-based learning on the gate selection level, we can do it on the gate generation level, and we can do it all the way down on the controller tuning level. So the point is, the autonomy stack can be leveraged in these much more, I don't want to say complicated, but much different applications where now humans are in the loop, but acknowledging this role of autonomy in the broader architecture can open up new avenues. And this ultimately will allow, we hope, these kind of understandings of autonomy in general to be deployed broadly speaking. So in this case, this is some earlier work that was in conjunction with Wondercraft, but this is their exoskeleton being deployed in a hospital setting. And the importance here, and why I'm showing this video and why I think this is so powerful, is that this is, I think, ultimately where we want to take autonomy is to real world environments. So in this case, just to be clear, these are complete paraplegics that are walking dynamically with an exoskeleton that uses algorithms that were inspired by the robotics community, for which we've collaborated with Wondercraft, among others. But this is where we want to bring these kind of autonomy features, is into real world environments that are complicated. And of course, on exoskeletons, but also on walking robots, right? So also on sort of fully autonomous systems where humans might be in the loop, might semi be in the loop, and might not be in the loop at all. And so that's really what's driving me forward in my lab, is to try to get these real world autonomy features widely deployed on real world systems and real world environments, for which I think the lessons of this talk are twofold. One is that formal control theory, nonlinear control theory, can play a significant role in guaranteeing safe autonomy at a formal level and also at a practical level. The second point is that we have to acknowledge the architecture is present in these systems and make guarantees across these layers in the architecture to really make these formal safety guarantees. And with those things together, there's a lot of power in unifying all these together, with, of course, experimental results being the backbone to inform the theory and develop new theory that in turn results in better experiments. So this is this is the biped walking over that root system where it fell earlier, and it just takes this root system on like it's nothing now, because we've made our algorithms better, informed by the failures we earlier had. So with that, thank you very much for listening, and it was an honor to talk at the workshop.
So the audience has any questions, please come up to the microphone.
Hi, thanks so much for the talk. I'm curious about how difficult it is to write these control barrier functions, especially for maybe like unstructured sort of settings. Yeah.
So the question was sort of the synthesis of the control barrier functions, right? Yeah, that's a great question, and that's another 20-minute talk to fully address. So I would say if you're trying to synthesize barrier functions for a really nonlinear system with input constraints, if you don't have input constraints, they're actually very easy to synthesize. But if you have input constraints, which we usually have, meaning actuator constraints, it can be complicated, and there's lots of methods to do it. You can use Hamilton-Jacobi, you can use this backup safe set calculations, etc. So there's lots of ways of approaching it for these very nonlinear systems that have worked well in practice. That being said, I think part of the power to autonomy, since it's an autonomy thing, is that by using these reduced order models to synthesize the barriers, just like a single integrator, double integrator, unicycle model, the synthesis of the barrier becomes a trivial thing almost. And so for the results I showed with the drone and the quadruped walking around the lab using barriers, in that case, you can write down on an envelope the barrier function. And then you're leveraging the autonomy architecture. That's where the complexity goes, is making sure you've layered the architecture properly, but the synthesis itself gets a lot easier. So I think, in short, there's a lot of work to be done on synthesizing them for general system. That has a lot of merit, of course, and it's a really interesting problem. But in an autonomy context, it gives you a way to synthesize them much easier if you leverage the overall architectures of the system, and you'll still get formal guarantees in the process.
Thanks.
Great question.
All right, let's take one more question.
All right, so these control barrier functions are ways to try to avoid certain sets that are unsafe.
Mm-hmm.
I was just curious, why not just have that set itself as a constraint not to go into? Why use these control barrier functions in order to avoid these sets?
Yeah, so why not just enforce, for example, you want H to be positive and the question then, how do you enforce that? I mean, do you check so you have to do like, let's say an MPC problem where you're making sure your evolution of your system is within that set at every point in time, which you could do, but that requires you solve an MPC problem, right? The advantage to the barrier functions is that it gives you an instantaneous check. Think about it like this. If you're driving a car and you want to avoid a wall, you don't wait till you hit the wall to stop. You're going to look at your speed relative to the wall and brake according to that speed. And that's what the control barrier functions are doing, is it's a velocity constraint that guarantees you won't hit the wall, but you can check well away from the wall. And by doing that, you can apply it to fully nonlinear systems where you still get an convex optimization problem for those nonlinear systems by checking this derivative condition. That's the short answer.
Okay, thank you.
Yep.
Cool. Let's give our speaker another round of applause.
For everyone.